Okay.
ठीक. Okay. So last time हमने बात की थी कंजर्वेटिव और नॉन कंजर्वेटिव फोर्सेस के ऊपर, एंड वी लेफ्ट ऑफ while talking about नॉन कंजर्वेटिव फोर्सेस. तो हम एग्जाम्पल कोई नहीं कर पाए थे फॉर अ नॉन कंजर्वेटिव फोर्स, so I thought why not let's do that. Let's start today's lecture with that. So, well, jumping right into the example, hum, let's consider that you have a heavy spherical ball-like object, say, and it's on a level ground. So let's say that this is some spherical ball, and it's a heavy ball. So let's say it's 65 kilograms, and it's moving on a flat leveled surface, right? So let's say it moves some distance, let's call that d, and it will come to a stop on a level ground. But now it's traveling initially at 6 meters per second. So it's moving in this direction. We'll say initial velocity would be 6 meters per second. And the force that is responsible for this ball to come to rest is 450 newtons. And so that force would be the force of friction, and it would be acting in the opposite direction to the motion, right? So the ball slides to a stop in some distance d, and in the process what happens is that friction removes ball की जो kinetic energy है by doing an amount of work, right? और वो work किसके equal होगा? It would be equal to the kinetic energy of the ball, right? Because there is no potential energy over here. And again, for the concept of non-conservative forces, we cannot define potential energy. So let's see. The friction force जो है, it is responsible to stop the ball. और वो कैसे करेगी? It would do that by simply converting the kinetic energy of the ball into other forms of energy, including thermal energy. So what happens is that the work done by friction is added to the kinetic energy, and that brings down that brings down the kinetic energy to zero. So this means that the work done by friction must be negative. And we can also check that simply by writing down the formula for work done, which we know is, well, we are talking about the work done by friction. So it would be the force of friction dot d. Now I can write this down as fd cos theta. I can write the dot product like this. और यहाँ पे जो एंगल थीटा है वो जो फोर्स है और ये जो डिस्टेंस है इसके बीच में जो एंगल होगा वो होगा, right? So it is the angle between the force and the displacement vector. And we can see that the angle between the displacement of the ball and this frictional force is of 180 degree. इस diagram से आप ये चीज देख सकते हैं, right? And so then I'll just substitute in place of theta, I'll substitute 180 degrees, and cos of 180 is -1. Cos of 180 degrees is -1. And so finally, I can write this thing as being equal to negative FD, right? Okay. Let me just change the settings क्योंकि वो मेरे टैब की स्क्रीन जो है वो बंद हो जाती है. Let me just increase this time to 10 minutes or so. ठीक है, let's continue. Okay, now all I have to do is use the work energy theorem, and that is half mvi squared plus, and now because this work done is negative, so I'd have negative fd, and this thing should be equal to 0. These are the only uh, energies that are there, right? The work done by this force of friction and the kinetic energy. और बॉल रेस्ट पे आ रही है, तो kinetic energy कम हो रही है by this amount minus fd, and it's bringing the ball to rest, and that's why we have 0 over here. Now just moving things around, we can have fd is simply equal to 1 by 2 mv squared, right? And this is the initial velocity. So our goal is to figure out what distance will the ball be able to cover until it comes to a stop. Of course, provided that when I looked at it initially and set my clock at t is equal to 0, तो उस वक्त बॉल की जो velocity मैंने देखी थी वो थी vi, or in other words, I wrote it down over here, it was 6 meters per second. Now, well, we have all the physics figured out of this situation. So let's just use this equation जो हमारे पास यहाँ पे है to compute that distance, right? जो ball cover कर सकेगी जब तक वो रुक नहीं जाती. So, well, it's very simple. You just have to put in values. So d would be from here equal to 1 by 2f mvi squared. Or if I put in the mass of the ball, that is 65 kilograms, initial velocity, which is 6 meters per second, and the force of friction, jo 450 newtons hai, I'll get 2.60 meters distance. So the idea of this particular problem was to give you the concept के जो amount of non-conservative work जो है ना वो it is equal to the change in the mechanical energy. For example, you could think of something like के आप compare करें a truck with a mosquito, मच्छर के साथ, and they are heading towards you, and the reason you can easily stop the mosquito but the truck would run you over is because of this difference in the mechanical energy of these two things, right? Okay, now let's make this same problem, let's make it a bit more complicated, and this time let's say कि जो ball है, it is sliding up the slope with some angle theta. So let's just make this slope. It's something like this, right? And it's inclined at some angle 5 degrees, and the height from the ground is let's just call it h for now. Okay. And this distance of this slope, let's call it s, right? Now the ball is sliding on the same surface as before, or this just tells you कि जो friction होगी ना इस surface के ऊपर वो same होगी जो हमने ऊपर problem में देखी है, which was 450 newtons. So we shall also assume a same initial velocity ball की इस surface के ऊपर, and let's say it was 6 meters per second. And again, हमारा goal ये है, it is to work out how far will the ball slide up this inclined slope until it comes to a stop. So this time, the work done by the non-conservative friction force on the ball reduces the mechanical energy it has from its kinetic energy when it's at it's at 0 height initially, right? It's somewhere over here. and to the final mechanical energy that it will have when the ball moves through this distance s over here to reach the height h along this slope. So, well, first thing is first, let's figure out what would that height be. And from trigonometry, it is simply this vertical component of the distance s that the ball will travel up the slope, right? So if I draw this triangle, something like this, and this is my s, this is 5 degrees. From trigonometry, I know that this side would be simply s times sine of theta, where theta is 5 degrees, right? Both chota likha hai. Let me just make it a bit bigger. So it would be s times sine of 5 degrees. Right. Okay. Now everything we can now write all of this that I just said in a mathematical equation using this work energy theorem. I'll have the initial kinetic energy plus the initial potential energy plus the work done by this non-conservative force should be equal to everything that is at the end, which would be the kinetic energy at the end plus the potential energy at the end. So ab you might be thinking in the previous lecture on conservative and non-conservative forces, I said we cannot define potential energy for a non-conservative force. So what the hell is this potential energy doing in this equation, right? But remember that the ball is sliding up the slope, and to do that, it must be doing work against the force of gravity, right? And well, we know that force of gravity or gravity, it is a conservative force for which I can define a potential, right? और तो वो potential जो है वो हमारे पास conservative force के लिए है. Right. Now, like before, the work done by the friction would simply be negative FD, or for this case, it would be negative Fs, right? And the potential energy initially is just zero, क्योंकि वो किसी भी height पे नहीं है, तो there is no work being done by gravity, and the potential energy is zero. लेकिन kinetic energy is non-zero और वो half m vi squared है, where vi is 6 meters per second, and at the end of its journey, when the ball stops, the kinetic energy just vanishes and it goes, all of it goes into the potential energy, or that would be mg. Now we know that potential energy is written as mgh, but h हमारे पास यहाँ पे क्या है, s sine 5, so it would be mg s sine of 5 degrees. Right. So with this, again, we have all of the physics of the situation figured out. Now we'll just use the equation that we had, that was Ti plus Vi plus the work done by the non-conservative force is equal to Tf plus Vf. By the way, if you have been following, this Ti is the initial kinetic energy, Vi is the initial potential energy, or this is work done by non-conservative force. Tf is again final kinetic energy, and Vf is final potential energy. I just said this because I figured if someone is new over here, तो मैंने last lectures में T को use किया था kinetic energy define करने के लिए, right? Okay, now let's look at this problem again. What would be Ti? वो हमें पता है कि it would simply be half m Vi squared, or Vi is non-zero, so Ti would stay in this equation. Lekin Vi would be zero because initially the ball is not doing any work against gravity, and it's at a zero height, of course, then. So Vi would be 0. Work done by the non-conservative force would simply be negative Fd or Fs, right? And this thing is equal to initial, finally हमें पता है कि हमारी बॉल जो है रेस्ट पे आ जाती है, तो final kinetic energy is 0, and we know कि जब वो it travels some distance or it moves up some height when it is traveling along the slope, traveling upwards along the slope, so it gains some potential energy, right? The kinetic energy is being converted into potential energy, or finally uski sari jo energy potential mein chali jati hai. So we have mg s sine of 5 degrees, right? And now everything is simple. You just have to compute s. We already know what f is. It was 450 newtons. And we know what vi is. It's 6 meters per second. And g, let's use 9.8 meters per second squared. Mass bhi hame pata hai, which is 65 kilograms. So all you have to do now is just put these values in your equation, and what you get for distance is that s would be 2.31 meters. Ab, let's compare this with the earlier case where जहाँ पे हमने इस वाले एग्जाम्पल की बात की थी, यहाँ पे सिर्फ बॉल it was sliding on the level ground. Ground was level and it covered more distance जो हमने compute किया था 2.60 meters compared to this distance that we computed, that is 2.31 meters, right? And so a question here arises, okay, why is that so? Well, you would expect that, and that's because here in this case there is work done against gravity as well, so the distance covered is less. So when both the conservative and non-conservative force acts on the object, we can make use of the potential energies of this conservative force and the net work done of the non-conservative force instead of applying Newton's laws. Because if you use Newton's laws, it's all about, forces, right? Or usme jo forces hai, you have to treat them as vectors, and so the vectors would be pointing in different various directions, so it would make the problem a bit harder, but the work energy theorem makes your problem much simpler, right? Okay, so well, with this, let's move to the topic of gravity, or let's call it gravitation. Gravitation, right? Okay, so we will do examples for gravitation hopefully in the next lecture. Let me just give you a brief or a long idea of what this gravitation or the law of gravitation is all about, right? So this law of gravitation is such a elegantly simple principle जो nature follow करता है, and it's so complete, and it just says that every object in the universe attracts every other object with some force, which for any two bodies is just proportional to the mass of each and varies inversely as the square of the distance between these two objects. So I can write it down mathematically as negative g, where this g is the universal gravitation constant. You can measure it as well. There was a physicist, English physicist named Henry Cavendish. I don't know if I pronounced that right. He made an experiment and measured this value of g as well. So you can look that up. And then you have the mass of two objects. So let's call them, let's call one of the objects mass with capital M और दूसरे की small m से denote करते हैं, and divided by r squared, where r is just the distance between these two masses, and of course it's in the direction of along this vector r. Right. Now, you might be wondering कि ये negative sign यहाँ पे क्यों है? And it's just reflecting the fact कि जो gravity है वो attractive होती है. And because the unit radius vector जो है ना, it is directed outward, तो हम negative sign से उसको compensate करते हैं, and we make this equation such that the force is attractive and not repulsive. We don't want gravity to be repulsive. We know it's not repulsive, right? So we add this negative sign. ठीक है. So let's just add another statement to this fact. An object, it responds to a force by accelerating in the direction of that applied force, and it's, you already know this, right? And it does so by an amount that is inversely proportional to the mass of the object. And with this, then we have we really do have everything that is required to well understand the idea of gravitation. So let's talk about Kepler's laws, and let me start with the story, which goes something like, okay, earlier there used to be philosophical debates about what went around what, right? So by that I just mean people used to argue about if Earth went around the sun or sun went around the Earth, or all those things, right? Well, it was done so until some guy, I cannot pronounce his name, Tycho or something, he proposed to study the position of the planets, and then with that try to figure out okay, what went around what. And he did that, but but after some time, well, he died, and after his death, his data that he wrote down was studied by the mathematician who's called Kepler, right? And he then discovered from the data of some of the very beautiful laws regarding planetary motion. Jo data uski thi, again, I don't know how to pronounce that name, Tycho or something, right? Now, first of all, or let's just say कि firstly, जो Kepler का जो first law था, Kepler found that each planet goes around the sun, and it does so in a specific curve, which curve is called an ellipse, right? Or the sun is at one of the focus of this ellipse. So an ellipse, let me just try to draw it something like this, right? And it has two points over here, and you call them focus. So well, let's say कि यहाँ से distance है r1, and इस focus से इस point तक distance है r2. Now, well, in one of the ways you can describe what an ellipse is, it's not just an oval or an egg, but a very precise curve that you can get by using two tacks, and you put them like this, or just place them that is के हर each focus के ऊपर उन्हें place कर दो, a loop of string and a pen, and you can draw this ellipse, right? Mathematically speaking, it is the locus of all points, the sum of whose distance from these two fixed points that are called foci is a constant, right? Okay, now secondly, Kepler also noticed that the planets do not go around the sun at same constant speed, but it happens okay, they move much faster nearer to the sun, and they move slower when they're away or further away from the sun. So well, to understand this, suppose that you observe a planet at any two successive times, maybe say a week apart, and the radius vector is drawn. That is, radius vector kya hai? It is just a line from the sun to any point in the planet's orbit, right? And it's drawn to the planet for each observed position. Well, let me just, I'm just speaking, let me just show you by drawing what I'm talking about. Okay, so let's say we have a sun is at this foci, and so once you observe it over here, so these are the two points where you observe it, and the time is the same when it's over here. So ये भी delta t होगा. Well, what I'm saying is that the orbital arc जो है, it is traversed by the planet during that well, one of the week, एक week जो हमने week का time लिया ना, and the two radius vectors, they bound a certain area, right? So this is the area. And now if two similar observations are made a week apart at one part of the orbit further from the sun, the bounded area is exactly the same as the one that is closer to the sun. So the orbital speed of each planet is such that the radius vector जो है, it sweeps out equal areas in equal times. And we can, well, if I take one of this vector, let's say this one is something like this, and this is r at t2, and this is r at t1, and the angle between these two vectors is, let's say, d theta, then this side would simply be it would be r d theta, and from this I can write down the area, or the shaded area that we are talking about, this one is simply dA is equal to 1/2 r squared d theta, right? So just using the area of a triangle. We can also go one step ahead and divide this with dt. So that would just give me dA over dt. And we call this dA over dt, हम इसे aerial velocity भी कहते हैं, and this would be equal to 1/2 r squared d theta by dt. Right, now finally, or let's say thirdly, the Kepler observed third law, and it was discovered actually much later, and it is sort of even different from these other two laws, and it is so in such a way that it deals with, well, not only one planet, but it relates one planet to another one. And well, let's just see. The law says that when the orbital period and the size of the orbit of any two planets are compared, so it turns out that the periods are proportional to well, it's proportional to the period is proportional to 3/2 power of the size of the orbit, right? And in this statement, the period is just the time interval that it takes a planet to go completely around its orbit, while जो size है, it is measured by the length of the greatest diameter of the elliptical orbit, right? It is also sometimes called the major axis, right, for an ellipse. And to put it even more simply, so you can understand it, let's just compare it with circles. So if planets went around in circles, which in fact they almost even nearly do, so the time required to go around the circle would be proportional to the 3/2 power of the radius, right? So that's simply for a case of circle. So with this, I can write down the 3 laws, and I let me even write these laws down formally as well. The first one was telling you about how the planets move, right? And it said planets, or every planet, they move in elliptical orbits about the sun. And of course, the sun is at one of the foci. So it's at one focus. Let's write one focus, right? And the second one we saw, it says that the radius vector जो is coming from the sun to the planet, it sweeps out no space over there, let me just, it sweeps out equal areas in equal intervals. Equal intervals of what? Of course, equal intervals of time, right? What that means is, well, कि जो area है, area covered or area swept per unit time is a constant, or it does not change, right? So the same area is covered in unit time. The final, or the third law, it says